So, Jill, in the first part of this question, it says, find the approximate sample size required to construct a 99% confidence interval for P that has a sampling error of 0.06. Well, first, let's think about the basic formula that we know for calculating a confidence interval for a sample or for a population proportion. We take our sample proportion P hat plus or minus our critical value Z star times the standard error of our sampling distribution, which is typically the square root of P times 1 minus P all over N. And if we don't know P, we use P hat. So in part A, it says, let's assume that P is near 0.3. So we're giving you, or they're giving you, a sampling error, which is this part of the confidence interval, equal to 0.06. So we're going to take that part of our confidence interval and set it equal to 0.6. And what we're basically doing is we are solving for N. So our critical value Z star, when the level of confidence is 99%, is 2.576. And if you need me to explain to you where that comes from, just let me know. They're saying, let's assume that we know that the p-value is near 0.3. So p would be 0.3, which makes 1 minus p, 1 minus 0.3, which would be 0.7. And we want to solve for n. So what we have to do is a little bit of algebra here. We have to divide both sides by 2.576. And I'm going to avoid rounding until I get a final answer. And that'll eliminate the 2.576 in front. Then we notice that our n is underneath the square root. So we need to square both sides of our equation because the opposite of square rooting is squaring. And that'll give us our 0.06 over 2.576 quantity squared. And when we square a radical, it ends up just eliminating the radical. So 0.3 times 0.7 is 0.21. And so we have 0.21 over n. Now, again, I'm avoiding rounding until I get a final answer. So a fraction squared is the same as taking the top part of that fraction and squaring it, and taking the bottom of that fraction and squaring it. So I'm running out of space here on this page, so I'm going to add a page. So I've got 0.06 squared over 2.576 squared is equal to 0.21 over n. At this point in time, we can just cross multiply. When we cross multiply, we're basically taking what's on top of the first fraction and multiplying it by what's on bottom of the second fraction. That would give us 0.06 squared times n. And we set it equal to the other cross product. What's on bottom of the first fraction, 2.576 squared, gets multiplied by what's on top of the second fraction, 0.21. Again, I'm avoiding rounding until I get a final answer. So n is being multiplied by 0.06 squared, so we undo multiplication by dividing by that number. And now we have n alone. N represents our sample size. If we perform that multiplication and then that division by 0.06 squared, we get an n equal to 387 point about 0.087. Now, whenever we're trying to determine an appropriate sample size for a particular sampling error, we always round our sample size up to the next integer. So we would need to sample, in this case, 388 people to ensure that if p is near 0.3, we would have a sampling error of 0.06 or less. In B, then, it's saying, let's assume that you don't have any prior knowledge about p, but you wish to be certain that your sample is large enough to achieve the specified accuracy for the estimate. So now we don't know that p is 0.3, and we rather just have to identify what would we need to take for a sample size to ensure that our sampling error is 0.06 or less. So what would change here is that we don't know that p is 0.3, so what we always do in this case is we use a p of 0.5, which makes our 1 minus p, 1 minus 0.5, which would also be 0.5. And when we multiply 0.5 by 0.5, we don't get 0.21, but rather 0.25. And then we follow the same procedure thereafter. We cross multiply and round our sample size up. And our sample size in this case would need to be 461. Be sure to let me know if you have other questions, Jill.